Well, here we are onward with our second part to the video. I'm going to jump just a little bit out of order in our notes and go immediately to the third page where there's a discussion of the graphs of parent square root functions and the parent cube root function, just so we're clear on some of those properties of the functions. Well, it zoomed in. Oh well. Oh, that's wrong already. Oop, mistake, mistake. So the domain of the parent square root function is 0 to infinity, every number that's non-negative, and the range follows suit with that. Whereas the domain of a cube root function is all real numbers as well as the range. I do want to focus just for a second on something that I meant to say in the last video, but I just didn't. This point of inflection right here, um, some interesting stuff happens here that I don't want to spoil. You'll get to it in calculus, but if you think of what the slope of a point, not actually, ignore it, rewind, never mind. So let's go ahead and just focus on what I'm trying to get at here, that um, general forms of each of these functions can be used, and transformations that we learned in Unit 1 back way long time ago at the beginning of the year can be used to also sketch the graphs of functions rather than just plugging in random points. That I'll remind you that the a value, the value right outside the radical, tells you one of two things. Whether or not the function is being vertically stretched or compressed, and it's stretched if that a value, the absolute value of that a value is larger than 1, and it's compressed if the absolute value of a is between 0 and 1, or another way of saying that is a fraction between 0 and 1. Um, it also tells us the reflection piece, and I didn't throw that in here, but it tells us a reflection over the x-axis, that if a is negative, then that graph is being reflected over the x-axis. The second piece here is the b value, which in these cases are either a horizontal stretch or a horizontal compression. And I'll remind you that changes on the inside of the function, where the function in this case is the radical function, are opposite of what we would think they are. So if b, yeah, I guess the absolute value of b, is between 0 and 1, then that means that the graph is being horizontally stretched by that factor. And the horizontal stretch meaning that the x values are growing by the inverse of that number, or the reciprocal of that number, not the inverse. Um, Whereas if b, the absolute value of b, is larger than 1, the x values are being compressed by that factor. They're being multiplied by 1 over b. Um, the c stuff is the horizontal shift, either right or left, based on whether or not that's a plus or a minus. And the D would be a vertical shift, either up or down, depending on whether or not it's positive or negative. So let's go to the back just a little bit. Example 4, where we're asked to graph y equals the square root of x plus 4. We should recognize that what that will look like is the graph of y equals the square root of x, that's the parent function, and it's that graph shifted right by 4 units. So exactly everything that the parent function, or every ordered pair that the parent function has, shifted left 4 units, which means subtract 4 from the x values. So while the parent function, I'm going to graph in, maybe I should do that in green. I'll do the parent function in green. Spice up the color. The parent function has these points. Let's see, 4, 2, 9, 3. Those are some of the points that are on the graph of the parent function. I'll even make it dotted for you. just so you don't think that's the actual function. Get some spice in your life, you know? Oh, I didn't dot the arrow. You gotta dot the arrow. We gotta be extensive here. Should I dot the points too? No, they are dots. Okay, let's just move on. That uh, a shift right for you. Ooh, I keep saying right. That's supposed to be left. Mistake. Left, 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 right, left. That's a shift left 4 units. Come on, Iman. I bet you guys are loving you're going to get donuts for this when you get back. Anyways, shifting left 4 units would mean take the point that's on the parent function and shift it left by 4 units. Don't shift it up or down, just left. Same with all the other points on the graph of the function. Left 4 units would mean here. 1, 2, 3, 4. 1, 2, 3, 4. And here's the new graph of the appropriate radical function. It's not expected that you go through all of these steps of um, of graphing the parent function first, so long as you can at least show the key features of the graph. You know, the zeros if there are any, the y-intercept, and 3 additional points on the graph. So in this numerical representation here, if I'm trying to think of convenient values to plug in to produce a y value that is an integer, um, maybe I choose -4 as one of my x values because -4 plus 4 is 0. The square root of 0 is 0. So 1 point on the graph should be -4 is 0. If I look at the graph, turns out that is true. Yay! What's another convenient value? Well, um, maybe if I choose -3, the radicand ends up being a 1 because -3 plus 4 is 1, and the square root of 1 is 1. So the y value should be 1. And that point right there. And again, this process is just fairly consistent, that if x is 0, then that's the square root of 4. Square root of 4 is 2. Oh, looky there, there's a point right there. And lastly, if I choose that x is 5, that produces a radicand of 9, meaning that the square root of 9 is 3. That's one of the points on the graph of the function. What's the domain of this function? Well, that's an interesting question. The domain can easily be determined for a square root function by thinking about the allowed values under the radical. If I look at the radicand in this case, right here, x plus 4, I have to know that x plus 4 is greater than or equal to 0 because it's not allowed for any value that's non-negative to go under the radical. Non-negative? It can't be negative if it's going under the radical. Um, from there, that gives us an appropriate inequality that we can solve to determine what the domain is greater than or equal to -4. Since x is greater than or equal to -4, that means the domain has to be all values greater than -4, including -4. The range doesn't change because there's no vertical shift in this case, so 0 to infinity. The endpoint does shift to -4, 0. If there are any questions, feel free to ask them now. Okay, I guess there are no questions. Let's move on to the next example. Um, the cube root function, keeping in mind that it does have 2 parts to it and the domain is all real numbers, maybe I can think of convenient values to substitute in for x that produce a whole number when I evaluate the radical. Well, let's think about this. -8 is a perfect cube. Therefore, what value would I plug in for x to get -8 under the radical? -5. So -5, if x is -5, then Evaluating the radical of -8, which is -2. -2 minus 1 is -3. 1 point on the graph is -5, -3. -5, -3. Oh, maybe it's always easy too to think about this in terms of the transformations. That's the point of these examples, that I know that the point of inflection of the graph happens at 0, 0. So if I can determine the the transformations of the point of inflection, then I have another starting point from myself. Um, this is a shift right 3 units and down 1 unit. So right 3, down 1. There's the new point of inflection on the graph, um, which happens to be at 3, -1. Some other points on the graph of the cube root function that's untransformed, just as a heads up, that's a general property of the cube root function and the square root function, that if the a value is 1, then as you go up 1 unit, right 1 unit, you'll go up 1 unit. Same with the other direction. It doesn't scale in the same way, that if I shift right 4 units, then I should shift, not shift, if on the graph I move right 4 units, 1, 2, 3, 4, then from that point of inflection I can move up. Ooh, that's even wrong still. Not 4, 8. If I move right 8 units, because this is the cube root function, I can move up 2 units. So 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. And there's the other piece over here. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. And from there, I can just build the rest of the graph. Um, while I often do leave space for the numerical representation, it's not my expectation that you approach it in that way. You're welcome to, or you can just utilize the transformations of the parent function. The domain, again, of a cube root or an odd index function is all real numbers, and the range is also all real numbers. Point of inflection we determined was 3, -1. And that's all I have for you now. We'll do some more examples.